Okay, let's see if it actually works in the way we expect it to work. So okay, so let's see what can we do here. We have the SQLite thing as usual. Okay, let's make a new database. It's called database about drugs. Okay, so we ask some people if they take drugs. Okay, and we know when they're born and their zip code. Okay, and I just wrote this now, so I don't know if it works. Then we add this to the table. Okay, we hope it works. And then we add these lines here. Okay, these are people that from another database, well, of voters. Just the name and address, well, not even the full address, just the zip code. Okay. Now these are the same people in our case, and we know it, and so some people take drugs and some don't. Okay, and so in theory, what we could do is first I have to insert these values here, right? Yeah, and then registration, and then voter. Okay, so this should work 1 through 3 values. Okay, so let's see if this works. Okay, so this is called database join. Does it give me an error? No, it doesn't give me an error, so probably it works. And then what we want to do is check out how you do the join. So let's check out the syntax. Basically select blah 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 and then join. Okay, it's the same as before. Oops, sorry. So it should be something like this. So select, let's say name, right? And do I have what it's called? I forgot to add a table here. Yeah. Put it before. That's fine, doesn't matter. So drugs text is not called drugs, it's called name. Okay. So the query is select from drugs and then join. I have to put this in an execute thing, and then join registration, right? And then there is a thing that we want to measure. Okay, in this particular case, it's birth is equal to birth, right? I think it should work. Let's try it. Table drugs already exists. It does.
Probably needs select star.
Yeah, but it says something already exists. Drugs. Interesting. Ah. Okay, let's start. Okay, let's have to read it again. Ambiguous column name birth. Okay, so I have to say that's particularly drugs birth and registration birth. Okay. Okay. And then what was the command for seeing what is? Yeah, I guess fetch all is fine. Move it again. Ah, nothing. That's weird. So there was nothing. What do you think? Am I doing something wrong here? But nobody's an SQL expert, so but they should work.
You could just try the natural join, perhaps?
Huh?
You could try just the natural join to see if you get a result. Instead of the normal join, just do a natural join between drugs and registration.
How?
Specifying.
Just join without saying anything. Okay.
Yeah, because they have the same column.
Okay. Yeah.
You have to do a
Yeah. Okay, let's try it now. Yeah, something happened, but I don't know why it doesn't print anything. But it does work, so let's look at this. I already have this, right? So okay, okay, so I got this. So now it should work. Okay. Okay, I got nothing. Yeah. So
you try writing natural join instead of string?
how do you do natural join?
Just write natural join.
Natural join? Okay, let's try it. Like without space? Okay. No. Something is weird. Okay, I'll solve this later. But this is supposed to work, more or less. So that's the idea anyway. So you could do it very easily if it works, if you knew the syntax. So which I don't. But let this be the thing to do for later. So anyway, so the problem with this thing is that even if you anonymize these guys a bit more, okay, so that this becomes just 99, so just remove this guy, right? So if I just remove this part, oops. Okay. So if I remove this part, okay, and also this, okay. So just know the first 3 digits, and then I remove these guys as well. Okay. Now these guys, these are the identifying features, right? So now if you do a join, well, you cannot really do a join anymore, but you can still match with this, yeah. And then you basically have a choice that, well, John Doe or James Madison, one of these people are taking drugs and the other is not. Yeah, if you know it's the same database, basically, okay. If you already know that James Madison is not taking drugs, then that means that John Doe must be taking drugs. Yeah. So it doesn't really help. So this is not identifying information. You have to keep this there, otherwise then there is no point to the database, right? So it's just the thing that you're trying to measure. Yeah. Okay. So how do we deal with that? Well, that's basically the focus of today's remainder and tomorrow's. Okay. So let's say that you want to contribute your data to some database. Yeah, that's me. And a judge also has some problem. Maybe they want to commit a data to the database. And then what happens is that somebody then publishes a study about this data. Yeah, it seems very nice and benign. You don't really see the data ever, right? You just see the statistics. Okay. That means that you should not be able to infer something about the individual data from the statistics that you see normally. But remember that this is just a function of the data. This pi here is a function of the data. So some functions are invertible, okay? So if you think that the function is a very complicated thing, you could just get the data directly. Yeah. You might be able to invert the function. Yeah. Most of the time this is not possible, right? But you can still maybe distinguish the result or the output of the function from two different variants of the data you could have. So for example, let's go back to the drugs. Okay, let's say that I'm taking drugs and the drug is not taking drugs, and somebody knows that and what you publish is the number of people that take drugs. Okay, if somebody already knows that judge is not taking drugs, then the number of people that take drugs is 1. That's me. Yeah. So if you imagine you expand this to 1,000 people, okay, if I know for the 999 people that how many take drugs, so I know it's 500, and then there is one person that I want to find out whether or not they're taking drugs or not, I can also ask them to be included in the study. I said there is 999 people. You will also say whether you take drugs. It's completely anonymous. You just throw a stone, a black stone in the box, or a white stone, depending if you take drugs. So nobody knows what you did. Okay. So then you count the stones, and it's 501. So you know this person is taking drugs. Okay. So it's all relative to the information that the adversary might have about you. Yeah. So it's hard to say how are you going to guard against this. It's not very obvious, right? Because if the adversary has a lot of information, then how much more can he get by seeing the output of your algorithm? Yeah, that's the basic problem here. Okay. So in general, you want to calculate something useful on private data. Okay, so it's useful to do the calculation, but people are afraid of giving the data for privacy reasons. So you want, first of all, have complete anonymity. We don't even want to know if you are in the data. Okay. So you cannot tell if you are even in the data, not your data actually, if you are in the data. Yeah, we want to hide that. Okay? You want secrecy, so even if we knew we were in the data, then there was no way you could actually extract your data. Even if you see the output of the algorithm. It's not very easy. It's not possible to have side information. Even if there is side information, then maybe the adversary gains a little bit more compared to when not seeing the output of our algorithm, but not much more. So it shouldn't matter what information they have already. They couldn't use this information to amplify, right, what they already know. So no amplification attacks. And finally, the most important thing, utility. Okay, so it has to be useful. If I just do a random thing without looking at the data, of course, there is no privacy problem, but I'm not using the data. So you have to use the data somehow to make the algorithms useful. Yeah. If you think about an example of a study like health study, then in general we find that the more people in the study, the better statistical results we get, and the less privacy we lose. Okay, when we calculate the study. So which is nice. Okay, so I will give a short example. It's again about drugs. I like drugs. So you have N athletes. Okay, it's a specific type of drug now, right? So you want to ask them if they take drugs. Right? And it's important to know if they take drugs for policing and for seeing if there's abuse in the sport and health issue as well, right? So you want to ask them, did you take drugs in the last year? And you want to calculate the percentage of people that dope. Right? Maybe it varies by sport or something. So the question is, how do you make them say the truth, right? You know, they can be worried that they write down the answer, well, it doesn't work, right? So it's not like they can go and vote in a secret way event. So what do you think? What is it? Has anybody seen this solution? There is a solution. No? Okay. So the solution is very simple. I ask you to take a coin, flip it. Okay? If it comes up head, you say the truth, or you write down the truth. If it comes up tails, you flip another coin, or the same coin, and then you record what the coin says. If it comes heads, you say the truth. You say 1, yes, I take drugs. If it comes up tails, you say no, I don't take drugs. No matter whether you really do take drugs, right? So then when somebody actually sees the answer, it doesn't know you said yes because you take drugs or because the coin came up heads, right? So it's a very simple idea. It was like 60 years old, I think, already. And it has been used a lot, and people kind of trust it, say, well, I can use this procedure, and people don't really know if I take the drugs. Right? So it's useful. And this is the first barrier you want to catch. Then how useful is the result, right? Yeah. So let's work this out. Let's try and work out how useful the result is going to be. Assume that the observed rate of positive responses in the sample is P. Yeah, so P are the positive responses in the sample. the rate. So you are 1, 2, 3, 4, 5, 6, 7, 8, 9 people. Okay, so if you 4, you say yes. I don't know if it's 2 or not, but 4 divided by 9 is your rate of responses. Okay, but in the whole population, it's let's say population of students in Oslo University. What would be the rate of drug use, given your answer? This will depend a lot on this randomization procedure, right? Assuming that you say the truth when you're supposed to say the truth. Do you think you can work it out a little bit in 5 minutes or so?
You can try at least.
Yeah, go ahead. So here, just work with expectations, so you don't have to worry about randomness here. Okay. It's easier if you start backwards. So if you know Q, then what would you get in expectation for P, right? If you knew Q, then what is the expected value of P?
Now
Q is the actual rate of people that. So then you can, if you calculate the expectation of P, then it's easy. We can start with expected value of P given Q. And that's
So, is it correct then the expected value of P is Q plus 0.25?
Q divided by 2, I think, plus 0.25.
Yeah.
Yeah.
Q divided by 2.
Yeah, so I'll just write it down here so everybody can see it. I guess it works or doesn't work. right? So the expected value of P, if we know Q, right? Okay. And that's basically, well, half of the time we're going to randomly say something, right? Yeah. And then half of the time we're going to say Q, right? So that's it. Yeah. So then that's 1/4 plus Q divided by 2, right? So if we write the other way around, then basically our P bar, let's call it, is going to be, or Q is going to be 2 times P bar minus 1/2, okay? So this 1/2 basically is our, well, this thing is kind of correct for the extra times we want to get the 1 or 0. Okay, that's fine. And then if you remember what I mentioned about concentration inequalities, basically you could also say that, well, you can also say something about what is the, let's say, an estimate. You can get an estimate, like a confidence bound or something for Q given P, if you know the procedure exactly. So you know the probability with which you get different values, so you can calculate exactly the probability with which you get a particular Q if you want, or a particular P. So you can estimate the probability of the Qs, but you have to have some prior normal, to do this properly. So if you think that the prevalence of doping in the sport is low, then you have a low concentrated prior on this. So it's something like this is kind of important to think about in terms of Bayesian inference and priors. So I think there's a low incidence of drugs in the sport or high, then you adjust your prior accordingly, because there's a lot of noise in this data in this particular example. So you have to take this into account. If you interview like 1,000 or 10,000 people, then it's okay. But if it's like 50 people, your prior information about how many people take drugs in the sport becomes very important. Yeah. So this added noise is actually making things very difficult. Okay, so let's see. Okay, I guess this was simple enough. So we can generalize this mechanism. Say that, let's take binary case. Okay, you have 2 possible values. Its individual I has 2 possible values, 0 or 1, no drugs or drugs, and there's a response either 0 or 1 again. And we can say that we are non-truthful, okay, with probability P, and truthful with probability 1 minus P. Yeah. So then we can adjust this depending on how much you care about privacy versus getting good results. If you get half is the maximum. It's not really the maximum. We could have the coin that comes up head 90% of the time. So then you say something random 90% of the time, if you want. So now if you think about the complete data, so you have a lot of people, right? And each one of them is submitting their own response. So you have a vector of responses. So you have a database. It's like a noisy version of the original database. So you could think about combining, let's say, the k-anonymity thing with this randomized data, if you like. It's still not completely nice because there are some things that are deterministic there. And this determinism is bad because there usually is some specific side information that an adversary can have, which basically makes it a requirement for you to have a random anonymization mechanism. If the anonymization mechanism is random, then whatever the adversary observes, there is always some probability with which he can be wrong in the guess that he makes. Think about it this way. So you can try and guess something from the data, but you don't know if the data is that way because of the input or because of the randomness. So the adversary always has to be somewhat uncertain about what the data was, just because of the randomness you add. The real question is how to add the randomness in the best possible way, to make the data useful, and maximize privacy. Okay, so in this setting, we can say that we can randomize every piece of data we have, let's say we can use exactly the same type of noise for all the data. So probability of seeing a specific output AI for specific data xi is always the same for when AI and xi are the same. Okay, and everything is independent. You just have this joint probability distribution. Now, let's work out on another exercise. So this is exercise heavy lecture. So let's say that the adversary sees it's not my data, but sees my output, okay? And he sees he believes that I have a 0 or a 1 in my hidden data. Okay. And then I use randomized response. So randomized response is defined this way. So probability 1 minus p, I say the truth, and with probability p I lie, or randomly lie, okay? Then what is the probability that my data is really 1 if he sees my response to be 1? Okay. This of course depends on the prior in some way, but it's useful to think about what is the actual posterior that the adversary would have. So with probability p, we say the other way around. 1 minus p, we say truth. Okay, so here we don't need to care about this part because we only have one person, right? So, Should I go over it now? Yeah. Okay. Right. So we said that. So here we're writing it like this. Yeah. So we can assign this to just be a number if we like. Okay. And this has to be. This is the prior probability that the adversary has of us having data 1, and because it has to sum to 1, and there are only two choices, x0 or x equal 1, then this has to hold, right? Now he sees that a equal 1, okay, and he knows that because of our policy, the probability that a equal 1 given x equal 1 has to be equal to 1 minus p, right? And the probability that a equal 1 given x equal to 0 has to be equal to p. Yeah, right. So then we ask ourselves, what's the probability that x equal 1, given that we have seen that a equal 1? Well, we use Bayes' theorem, which basically says x equal 1 times the probability that a equal 1 given x equal 1. Okay. Now I have the same term again. Yeah. Plus the other case, x equals 0, x equals 0. Okay. So this basically is, well, let's call this guy something. Okay, let's call it I don't know, gamma, right? So we don't have to write again. No? So it's gamma times p equal 1, x equal 1 is 1 minus p, right? And then have the same thing here. And then this is going to be 1 minus gamma, right? And this is going to be p, yeah? Yeah. So if we want, we can rewrite this in some ways, but basically what we get is that the probability of this guy, so this will increase, right, when he observes. So this thing will be greater than gamma. Yeah. Actually. Okay. So it has some prior probability of us saying the truth, also, of us taking drugs, and then when he observes it as saying a 1, then this will increase. But how much increases depends on this p, right? So when p is equal to 0, so we never say a lie, right? Then this becomes a 1. Yeah. If we know that p is equal to 1, so we always say something randomly, then it doesn't change anything at all. Yeah. So that's basically it. So when p is very small, then he believes more the data that he sees than when p is very large. And that's basically the whole idea of seeing it from a Bayesian point of view. So you can see the side information in this case as a prior distribution on what is the truth, on what's the data. So you can think of the adversary as having a prior distribution on the data, and then he sees something, and then from what he sees, he has a posterior distribution. Okay, and then the whole idea of differential privacy that we'll explain very briefly now, before we go into it in detail tomorrow, is that no matter what adversary knowledge, he cannot increase his probabilities on any possible data set by more than a constant factor. Yeah. So that's the basic idea, formally at least. Okay, so this is what we call the local privacy model, because here every person has their own data, and their own data is individually randomized in some way. And these people have actually created the concept of differential privacy. I guess this is Cynthia, this is Kobe, and one of them is Adam Smith, and one is Frank McSherry. And the idea is that you have some algorithm, okay, and this algorithm is such that when the inputs to the algorithms is similar, so you have one database X and another database X prime, and they are similar can define similar any way we like, then the probability of seeing the same output for slightly different databases is very similar. So the output of the algorithm is kind of smooth with respect to database changes. So if I just change your data or I remove you from the database, then the algorithm will give the same output with high probability. So it will be very hard for anybody to then figure out whether you are in the database or not. Yeah? Because even if you knew everything else about the database, so if you knew exactly what everybody's data was, okay? Let's say he knew everybody's data apart from yours, okay? You can imagine every possible data you could have and put it in the algorithm and see the probability of getting different outputs for the algorithm. Still, the probabilities of getting different outputs, no matter what your data is, could be very similar. So in this sense, the two different possible databases of you being in the data and you not being in the data have very similar results in probability. Okay? It's not like they are similar results deterministically, because then you could still tell the difference. Maybe the output is 0.01 if you are in the data, and it's 0.11 if you're not in the data. You can still make the difference because it's just a number, right? You can see the difference between two numbers. But if it's probabilistic, then he sees something he doesn't know if it's really because of somebody being in the data or not. Okay? So this is the way I formalize it, saying that the logarithmic ratio of the two probabilities for data where one person is in there and one is not is bounded by a constant. Okay? That's the basic definition. There are even more definitions, but this is the strictest one. It's very strict. And when we say neighborhood here, we mean that usually that in one case there is a data of one person in the database, in the other case there is not. Otherwise they are identical. And these databases are considered neighbors. Okay? So if you want to consider, let's say, constructing a database from scratch, so the empty database would be one database, and then when you add one record, this is a neighbor to the first one. When you add one more person, this is a neighbor to the second one, and so on. Okay. And then when you alter the data of one person, it's like you remove one person and you add another one. It's like two neighbors. So I think about it like this. Okay. This is the standard definition. It becomes a bit more complicated in general settings, but if you think about matrix data like tables, it is okay. Yeah. Now, why is this an interesting definition? Well, it was the first mathematical definition of privacy that actually made sense. And because sometimes it's very strict, so you cannot do a lot of things with it. There are various relaxations that allow more loss of privacy, but which make for you more useful algorithms. There's also a connection to learning theory. So because any learning algorithm that is differentially private in this sense, in the sense that you have some data and you get a neural network, right? So the input is the data and the output is the neural network. So if the neural networks are similar, or the distribution of our neural networks is similar with respect to the data, then you can have differentially private neural networks. And people have shown that you actually get better generalization ability if your algorithm is differentially private. It also helps with reproducibility. So if you are tuning your parameters in a holdout set, you can use an idea based on differential privacy so that you don't actually learn the holdout set, because it's also possible to learn the holdout set if you test enough. It's actually starting to be used now. So Apple was the first one to actually announce something about differential privacy. People haven't verified formally that it's what it is correct, but they have seen informally that it kind of makes sense. Google has an open API called Rapport, I think, which allows you to report data to applications using differential privacy, and uses this an extension of this randomized response mechanism that we mentioned. Uber is using it. They have an open source framework for SQL-based differential privacy. It's not perfect, but kind of first steps. And one of the big users is the US Census, where they record personal information of people in the United States, and they want to make sure that they ensure privacy. And one of their goals is, well, they have some statistical goals, so they want to maximize the amount of privacy they can have while making sure that the statistics they collect are useful. You know? So this is their goal. The maximum privacy for a given level of accuracy. So it's a big research topic these days, and there are many problems. One is the complexity. If you want really an efficient mechanism that doesn't waste data in some sense, and that does not too much noise, it's complicated to do. And the second is, how do you actually verify that things are implemented correctly. Yeah, it's very far from being trivial. If I give my data to Google or Apple, they say they're doing differential privacy or something like that. It's hard to verify that it's actually what they're doing. Yeah. Okay, so before we finish, for today, I will just show that if we are using randomized response, okay, and the p that we say is less than a half, so we say truth more often than not, then the definition satisfies differential privacy. So now we have no data from one person, but we have data from many, many different people, okay? And every person has their own data, x1, x2, x3. And we consider neighboring databases in the sense that the data of one person is changed. Okay? That's how we consider it here. So slightly different from saying that they're removed, but it doesn't make a big difference. It's like order 2 of neighbors in the case of removing or adding people's data. Okay, so we want to say what's the probability of having a specific output, which is a randomized database, given the original database. Okay, so we have independence. So the probability of a specific output for a specific person is independent of everybody else. So we just write it as a product. Okay, and then just remove. Okay, oops, I forgot something here. Anyway, this should be without the prime here. That's mine. So the prime should be on that side. Probability of specific AJ, the specific output for the jth person, given the data of the jth person, and then the data of all the other people. Yeah. Now, we have basically said that the probability of seeing the same data, right, as if xj and xj are different, right, then has to be p. Yeah? And if you do the same calculation for the other guy, you will see that the ratio is p1 over 1 is p. And actually, calculation from whole square, because the probability that aj equal k if xj equal k is 1 minus p always, because that's how we define the mechanism. So we want to basically find the ratio between paj given xj and paj given xj prime when they are different. And this is the maximum of these two fractions. Yeah. And this is always smaller than 1 minus p over p. So now we can use this to produce an inequality here. Yeah. Because this ratio is always bounded by this one for p smaller than half, then we can just basically use this as an equality for that. Okay. But now this one is basically PA given x is basically PA given the new data x prime multiplied by this ratio. And if you remember the definition of differential privacy, it says that the logarithm of the ratios, right, is bounded by a constant. Okay. Or if you look at it in the other way, the ratios are bounded by the exponential of this. Yeah. So that's saying the same thing as saying as the logarithm. Yeah. So there's a definition here. Okay. That's weird. What's happening? It's weird. Ah, I know what happened. There are too many pictures and it slows down. So you have the logarithm of this ratio, you take the exponent, just the ratio divided by smaller than the exponential of epsilon, right? Yeah. So this is the same thing we have. If you take the ratio of those two things, then these terms cancel out, and you end up with the logarithm of this divided by that, and the logarithm of this. So we're the logarithm of this differential privacy. Okay. And this is the first differential privacy mechanism we're going to talk about. And tomorrow we'll talk about the general query model, where you imagine you have a database and you're asking queries, but you want the responses to be private. Yeah. So this was a model where you just get a database that's randomized and you do whatever you like with it. Okay. We'll have some work problems to go through. So the problem with differential privacy is basically that there is not a lot of toolboxes there for you to work with. So we can only work with very simple problems and very simple approaches right now, but I expect this to change in the next 2-3 years. So anyway, thanks.